Hello everyone and welcome to my video on MATLAB. So in this screencast we'll be talking about how to fit the curve y is equal to mx plus c using nonlinear least squares to a set of experimental data. So this is our experimental data. So x goes from -10 to +10 and y varies as follows. The x and y values have been plotted in Excel, and our task will be to fit the curve y is equal to mx plus c to this set of data. Okay, so we know that y is equal to mx plus c fits this data satisfactorily, but the thing is we don't yet know the values of m and c, which the straight line will pass through these set of values. And so we have to instruct MATLAB to find m and c such that the straight line um, formed by y is equal to mx plus c passes through this particular straight line. So I plotted the experimental data in Excel. So this is x, this is y. I plotted x and y, the pairs of x and y in Excel. So the horizontal axis is the x-axis, the vertical axis is the y-axis, and we want to um, fit these. We want to find a curve which fits these um, data points. So the curve would be of the type y is equal to mx plus c, and as you can see, for different values of m and c, um, the resulting curve would be different. For example, if y is equal to 5 and c is equal to 2, we would get y values like this, which is quite different from the y values of the original experiment. Okay, so for x is equal to -10, the experiment has a value of 18 minus 18.1. If you put -10 into the equation y is equal to 5x plus 2, you'd get -48, which is quite different from -18.1. Similarly, if you put -8 into y is equal to 5x plus 2, you'd get -38, which is quite different from the experimental value of -13.4. So let's do a whole plot of all these values. I'm plotting the experimental, I mean the y values of the experiment, the y values of the straight line when m is equal to 5 and c is equal to 2. So I've assumed m to be 5 and c to be 2, and I'm just seeing if that particular assumption gives me a straight line with a good fit. So let's try and insert a chart. Okay, so the blue line that you see here is the experimental data, and the red line that you see here is basically the line y is equal to 5x plus 2. I've taken m to be 5 and c to be 2. So as you can see, at almost every point in x, there's a considerable difference between the experimental data point, which is in blue, and the predicted data points, which is in red. So at x is equal to 10, okay, y is around, the experimental data is around 24.5. Okay, so you can see 10 comma 24.5, and the predicted data from y is equal to 5x plus 2 is 10 comma 52, which means there's a difference of around 25, which is almost double the value of um, the experimental data, which is in blue. And obviously, our choice of m is equal to 5 and c is equal to 2 is not very good, okay? Because there is a difference between the experimental and the predicted data. But what if we could find a way of optimizing M and C using this data? Okay, so what we do is find out the difference between the experimental data, the actual raw data we have, and the predicted values. Okay, so what we um, what needs to be done is calculating the differences between the experimental data and the model predicted data, and using this difference to find a new value of M and C which would fit the data in a much better fashion. So if we could find, so the farther the data, the predicted data is away from the model data, the farther, the worse is the approximation of M and C. So how do we know M is equal to 5 and C is equal to 2 is a bad choice for the parameters M and C? Well, because there's a huge difference between the predicted data. Okay, so now we can change M and C to such a value. Um, so the degree of change in M and C, so we have to change M and C now to a new value so that the new values of M and C create another straight line which is much better, much better, which has a much better agreement to the model data. So so what we do, so let's try another guess of y is equal to mx plus c, and m is equal to 1.8 and c is equal to 3. So we see that there's a much better um, agreement between the experimental um, and the model data. Okay, so instead of minus 48, we have now minus 15, which is much closer to minus 18.1 here. Okay, instead of minus 38 at x is equal to minus 8, we have 11.4. Okay, so if we plot all of these together, we would get, I'm sorry, if we plot all of these together, we would get there's some error. Okay, so if we plot all of these together, okay, so this, we have to plot this. Okay, so yes, so this is the plot. The gray line is basically y is equal to 1.8x plus 3. Okay, the gray line that you see here, which is really pretty close to our experimental data, which is these points. So um, when m is equal to 1.8 and c is equal to 3, um, we have a much better fit of the data. But how did we get from m is equal to 5 and c is equal to 2, which is a very bad fit, to m is equal to 1.8 and c is equal to 3, which is a much better fit? So you can see in the case of m is equal to 5 and c is equal to 2, the difference between the experimental and the model, the experimental and the model data is large. So what MATLAB would do is use this difference and this difference and the square of the addition of these differences, which is basically the um, sum of square of these differences. It would use these differences to change m and c in such a way that it would come closer and closer to um, m is equal to 1.8 and c is equal to 3. It could go even better than that, but this is just the beginning. So you see, MATLAB knows how to change m from 5 to m 1.8, c from 2 to 3. So it can use this difference between, this is called the error. Okay, so it uses the sum of squares of the errors. Why is this called the error? This is an error because it's a deviation from what the value is supposed to be and what it is. Okay, it uses this deviation to calculate the new value of m and the new value of c, which would the curve fit the experimental data in a better fashion. Okay, so how does it do it? So how do we instruct MATLAB to do it? So let's look at MATLAB. Okay, so there are two important files that we need to do in order to do the nonlinear least squares. One is the function file. Okay, so this function, the output of this function is basically the difference between these two, the difference between the predicted data and the experimental data, which is the difference between the red line and the blue line, or the red line is basically y is equal to 5x plus 2. So the function my fun would find the difference between um, each of these values, um, each of the points, this point and the blue point here, this red point here and the blue point here, the red point here and the blue point here. So it would find the differences of each of these points and store them in an array. So for example, the difference between minus 48 and 18.1, that would be is equal to d5 minus c5. Okay, so that's the difference between this point and this red point and this blue point. Okay, I'm sorry, this red point and this blue point. That's minus 29.9. So if we drag this, so these are the difference. This is the minus 24.16 is the difference between um, minus 38 and minus 13.84. So basically we are finding the differences between these the the model data and the experimental data. So we need to feed that into MATLAB. Okay, so this particular column is basically the differences between these data, and we have to feed that into MATLAB somehow. So basically the myFun function does basically that. So it finds the model data, which is the red line. So if basically P1 represents M here and P2 represents C here. So if you put P1 is equal to 5 and P2 is equal to 2, and basically 5 and 2 are the inputs to the function, and the output of the function would be this whole column. Okay, it would just find the differences between the red line and the blue line. Okay, so let's try calling the function my fun m is equal to 5 and c is equal to 2. Okay, so what would the output be? So as you can see, the output is minus 29.9. So you see here minus 29.9, minus 29.9, minus 24.16, minus 24.16, minus 18.42, minus 18.42. So basically the function myFun, okay, so myFun, if you put the value of m and c into myFun, okay, the output is basically the differences between the model data and the experimental data. Similarly, if we were to subtract these data, the differences between um, the gray line, which is another model data, it's better, it's a better approximation than the red line, but it's still um, a bit, it's still some way to go to the experimental data. It's not exactly the same, but it's pretty close. So if we were to find the differences between this data and this data in Excel, we would do this. We would do E5 minus C5. Okay, so we would get 3.1 minus 15 minus 18.1 is 3.1. So we do the same thing for all the columns, all the rows. So minus 11.4 minus 13.84 would be 2.44, minus 7.8 minus 9.58 would be 1.78. So this column is basically the difference between the gray line and the blue line. Okay, so let's see if we if we put m is equal to 1.8 and c is equal to c is equal to 3 into myFun, let's see if we would get the same differences. Okay, okay, let's type myFun, m is equal to 1.8, c is equal to 3. Okay, so see, get the same differences, 3.1, 3.1, 2.44, you get 2.44 here, 1.78, 1.78 here. So myFun is basically, if you put m and c into myFun, the value of m and the value of c into myFun, it would subtract, it would calculate the model predicted data, subtract it uh, from the actual experimental data, and tell you the result. So it's telling you the result 3.1, 2.44, which is basically what we got right from Excel. Okay, so it's telling you the correct answer. So we somehow need to instruct MATLAB to use this difference, okay, and calculate the subsequent values of m and c, which would um, correctly predict the experimental data. Okay, so I hope the purpose of the myFun function is clear right now. So how do we write the myFun? So this is a function. A function basically has inputs, which is basically m and c in this case. So the input is a vector p, which, as you can see in this example, was m and c basically. So it takes an input of m and c. So it takes in just two values, m and c, and then uses whatever, the thing is, whatever you input here, okay, inside the arguments of myFun. Okay, for example, if you say myFun in brackets 1.8 comma 3, this gets passed on to p, and then p of 1 becomes 1.8, and then p of 2 becomes 3, and so you're basically doing 1.8 into x1, which is basically the x values here, plus 3, which basically gives you these data. Okay, and then you subtract it from this, which is basically this. So basically you're doing a subtraction of this with this, so you get the differences as stated here. Okay, so I hope you understand this. So basically p1 and p2 are basically the inputs to the function myfun, and p1 is m in this case, and p2 is c in this case. So you get the differences between the model and the experimental data from this particular function. It says so what next? So this is the main function. Okay, so this is the main function. X naught would be basically the initial values of m and c you give MATLAB. Okay, so you're instructing MATLAB to say, you're telling MATLAB, hey, this is the best uh, values of m and c I could come up with, which I think is um, the best solution, is close to the actual solution. So what happens is um, it it uses the values of x naught, inputs it into myfun. Okay, so you just saw that um, we were using um, we were inputting m and c into myfun to get um, the differences between the um, experimental data and the model predicted data. Okay, so what MATLAB would now do is take the initial guess of 5 comma 2. It would take m as 5, c as 2, calculate the difference, send 5 and 2 into myfun, calculate the difference, see if the difference is close to 0 or not, and if not, it would change x naught once again, and then check myfun and see it if it becomes close to 0 or not. And then this process continues and continues and continues, and then at the end, when myfun um, becomes minimum, okay, so myfun outputs the difference between the model predicted and the experimental data. So um, MATLAB ensures that myfun becomes minimum, and when myfun becomes the value, the output from myfun becomes very low, and it is then when MATLAB stores the value of m and c into the value param. Okay, so let's run this. So let's type run. So param becomes 2.13, 3.2. So that's it.